Oh, good afternoon. It's 2:36. We're actually 6 minutes late getting started. I had a phone call right before I was leaving the office, so I didn't get to leave when I wanted to, and then went down to the restroom before I came to class, and then saw something had been left in a classroom, and I went by the lab to tell someone. And so anyway, it took me longer to get here than I wanted to. But anyway, let's go on and get started. As you can guess, I'm the only one in here. Hopefully some more will be coming in later. Trying to start from current slide, but I can't get it to open. There we go. All right, we are in 2.5. Chapter 2 is first order differential equations, and 2.5 was substitution. And we got through the homogeneous equations on page 72 and most of 73, and then had gone to wanted to start today with Bernoulli's equation. So here is not quite the same as what we were using before. This looks like a linear equation, but it's not, okay? And here's what it is. Let me get my pen set up. If I can find the, there we go. All right. dy dx, there's your derivative or differential, okay, plus p of x, y is equal to f of x. Now, if it stopped right there, that would be your classic linear differential equation. Derivative to the first power, y to the first power with some coefficient function of x, and then on the other side, a function of x. But what makes this different is now we have another y to the n over here. Whoa, that is definitely not linear anymore because of that y to the n. Now, this isn't how you would normally write a differential equation. You'd probably have all the y's together, but this is written in the form that you'll know where n is any real number. In other words, it could be positive, negative, fraction or decimal, rational or irrational, okay? But this is called Bernoulli's equation. Now, I don't know which one of the Bernoullis this was. They say here in the book. I don't think they do. There was a whole family of Bernoullis that were, many of them, very bright, very well published, I'll put it that way, family of mathematicians and physicists from Switzerland. There were two brothers, Johann and Jacques, I think, James, Jacques, something like that, and Johann, okay, which is more like John, okay. They were each extraordinary mathematicians and physicists in their own rights, and at least one of them had at least one son who was also a very bright mathematician and physicist. And it sounds like they, being as bright as they were somewhat dysfunctional to the extent they fought like cats and dogs. They competed with each other. That's probably what helped make them bright. The father of the son, the story that I heard sometime or another was that there was this competition they had periodically in Europe that anyone could participate in. It was a math or science or some sort of competition. And he was so good. He was like the top in his generation, you know, mathematicians in Europe. And he usually won the prize because he was that good. And he had entered it this one year and thought for sure he was going to win, and it wound up he came in second. The sad news was he came in second to his son, and he didn't even know his son had entered the competition, and he got so mad he kicked his son out of the house. You know, he said, if you're that good, you can live on your own from now on, or something. Whether that actually happened, I'm not sure. But evidently they were very competitive and extraordinary bright family. There's Bernoulli's equations, Bernoulli's law, there's stuff all over physics and math after the Bernoullis and never can tell which one was which. Okay, so this is Bernoulli's equation where n is any real number. Note that if n is equal to 0, you've got your linear equation. Okay, for n equal 1, you've got a linear equation. Okay, either one of those would work. But if n not equal to 0 and not equal to 1, here is the substitution you would use. U is equal to y to the 1 minus n. Okay? A different kind of substitution here. Okay? Now, if that is your substitution, then let's rewrite the first equation. Okay, well, we probably need to do this too. du is equal to 1 minus n y to the minus n dy. Okay? All right. Then what we would have, dy dx would then become, let me make sure I proceed the same way they do. They don't do much, do they? All right. Then let's write this as y to the n du over 1 minus n is equal to dy, and this would be u is equal to y times y to the minus n. So y to the n here over y is equal to u. It really isn't helping very much. So let's do it slightly differently here. Y to the n is equal to u times y. Okay? All right. That's not u to the y, it's u times y. Okay. Now, let's see what we got. Dy dx, I'm going to put this y in here. That's not what I want. Okay. Okay. What this leads to is 1 over 1 minus n, and y to the n is uy, so let's do the u du Okay. I think what happens here, and now that I've been fighting for this for a while, I think it'll all come out a lot clearer if we actually put in a value for n. So let's erase this for now. I thought we were going to come up with a more usable form, but I think what we do is just use this substitution. Okay? And let's not try to come up with anything else. That's going to be our substitution. Let u equal y to the 1 minus n. Okay? Now, and that would be Bernoulli's equation. All right. So let's now go to example 2, and we'll see if we can get it to make more sense. Here's our problem. X dy dx plus y is equal to x squared y squared. Not a linear equation, because you have, and not in standard form anyway, you have an x coefficient here we don't want. The y there is fine. The x squared we don't really want there either. Well, no, the x squared is fine there. It's the y squared we don't really want there. And if we were to divide by y squared, we don't have it anywhere close to a linear form. So here's what we're going to do. First, it's not in standard form for even Bernoulli, so what we're going to do is divide each term by x. Okay? So there we have it. So what we have now is dy dx plus 1 over x, that's your p of x, times y is equal to x y squared. Okay. Now, the x over there is fine. What's not fine is that y squared. So here's our substitution. Let u equal y to the 1 minus n. Well, n here is 2, and 1 minus 2 is y to the minus 1. Okay. Now, then du is equal to minus y to the minus 2 dy. Okay? Now your dy dx becomes, so let's rewrite this as dy dx is equal to y squared du dx. Okay. Now, so this will become y squared du dx, that's your dy, plus y over x, or 1 over x dy, okay, equal okay. I messed up here. Wait. Yeah, no, it's fine. Okay, sorry. X y squared. Okay. Now, what we're going to do now, hey. Thanks.
I'm still working on it. I should have that one.
Oh, you mean linear algebra?
Yes.
Okay, right. Okay, good deal. Okay. Just had a student come in, but didn't stay very long. Okay, so let's see what we've got now. Let's divide everything by y squared. So we have du dx plus 1 over y, 1 over x times 1 over y is equal to x, because you're dividing by y squared. In this form, but remember 1 over y is u. So this is now du dx plus 1 over x u is equal to x. And that is indeed a linear form. Okay? That is a linear form. It wasn't just happenstance. Because of the way we chose the variables, this is what comes out being. Okay, now, so your p of x is equal to 1 over x, and what do? You integrate that dx. Okay, well this becomes, the integral becomes log x. Okay, then what you do, you raise that to the e. Well, e of log x is just x. That's your what do they call it? It's a multiplier, but you have a special name for it. Yeah, go and blank on what you call it. Integrating constant, integrating factor. Okay, you multiply that by each side of this thing. So this has x du dx plus u is equal to x squared. Multiply that by all three terms there. Well, this should come out being a perfect derivative. And if it is, it's d of your integrating factor x y. Or, I'm sorry, u, not y. We got out of y's, and we're now in u's. Okay. Well, let's see if that's indeed true. Yuck. Okay. This stinking thing gets all lost in the sauce. Okay. Is that a perfect derivative of that? Will that be x times du plus u? Yes, it is. So the integral of that is the integral of x squared. Okay? Well, this is x times u is equal to x cubed over 3, and then you divide both sides by x. U of x is equal to 1/3 x squared. And let's go on and put in our plus c here. I probably waited too late to put it in, but I don't think it really matters too much on this problem. Now, what is our u? It's 1 over y. So 1 over y is equal to 1/3 x squared plus c. I think I will want to change that around some. So let's put that 1/3 of x plus c. Let's keep the plus c with that. What we were calling c is now c over 3. So it's just a constant. And then let's invert and multiply, or invert that, and you have y is equal to 3 over x squared plus c. I think that's our one parameter solution. Let's see what they got in the book. Okay. All right, we started off the same. Okay. And here's Dan. Okay, turn on the light closest to me. Get you up. I'll turn on the projector, but let me mark you here. Yeah, I was going to do that next. Okay. Can't think of anything too new. I was just going to town on this one and then realized I left off a step. So I think I'm going to start back over at the beginning and walk through it since you just came in, rather than showing you the error in it, though most of it was right. I want you to see it correctly. This is example 2 at the top of page 74. This is Bernoulli's equation. And spent probably too much time starting to try to derive it. Then I realized they didn't derive it, they just used it. Okay? And here is your example. X dy dx plus y is equal to x squared y squared. Okay. Now, Bernoulli's equation looks like a linear equation. If you flip back one page, the left-hand side looks just like the standard form for a linear equation. The problem is the right-hand side has a y in it, which wiped it out from being a linear equation. But it's y to some power. But that n doesn't have to be an integer, not even just a positive integer. It can be any real number. Fraction, decimal, positive, negative, fraction, decimal, rational, or irrational. The n there. Now this example we have here is not standard linear form, even on the left-hand side. So we need to get the left-hand side to look like a linear. Well, what that requires is dividing everything on both sides of the equation by x. Okay? So that goes out and you have dy dx plus 1 over x times y. That looks linear. This still isn't. This is now x y squared. Okay? But it looks, that is Bernoulli form, because now the n is equal to 2. And that is Bernoulli's form. Okay. Now, your substitution that they told you for Bernoulli's equation, this section is on substitutions, and the substitution to use is let u equal y to the 1 minus n, where n is whatever your was here, and that was the 2. Okay? So, therefore, our substitution would be let u equal y to the 1 minus 2, which would be minus 1. Y to the minus 1. Okay? Okay. If you flip back one page, it says, for Bernoulli's equation, note the n equals 0 would be a standard linear form, so you wouldn't need Bernoulli's equation. N equal 1, you could get to standard form, so you wouldn't need it. But for any n not 0 or 1, and 1, for instance 2 or 0.5 or anything else, negative 0.3 pi, or anything else, you can use this. And that will be your substitution. Let u equal n to the 1 y to the 1 minus n. Okay? And in this case, your n was 2, so it would be 1 minus 2 is minus 1. So let u equal y to the minus 1. Okay. Now, what we have now, except we've got a little bit of a problem here. Now they go on and write it this way. I've already written it that way. Now here's what they're going to do next, okay? We need to substitute in this dy dx, okay? And before we can do that, we need to sort of chain rule it, okay? Dy dx is equal to dy du times du dx. Now this is a part I sort of glossed over before. I needed to put this step in. So we need to know what dy du is. Okay? Well, I want to change this to be y is equal to u to the minus 1. Just reverse them. multiply both sides by y and divide both sides by u, right?
Okay,
Okay. Here's our substitution, that one, which is u is equal to 1 over y.
Right.
Okay. I want y as a function of u, so I'm going to change this, just reciprocate both sides of y is equal to 1 over u. Okay? Which is u to the minus 1. Now, I wanted to leave it in u to the minus 1 because it's easier to take a derivative. So your dy du then would be, so dy dx is equal to, okay, take a derivative of that, that'd be a minus u to the minus 2, right? That's dy du times du dx. Okay? Make sense? All right. Now, we take that and plug it in here. dy dx is that. So minus u to the minus 2 du dx plus 1 over x y is equal to, whoops. We want to plug in what y is. Okay? Y is 1 over u. Right? From up here. Okay? Is equal to x times y squared would be 1 over u squared. Okay. Well, this thing right here is the same as 1 over u squared. Right? Negative 1 over u squared. So let's multiply everything on both sides by minus 1 over, by minus u squared. Okay? So this will be by minus u squared. This will be by minus u squared. Okay? Everything. So this minus and the minus go to plus, and minus, let's see, u squared over u squared would be 1. So this is du dx plus, your 1 over x stays the same, 1 over x. Now, what happens here is that plus becomes a minus because of that minus, okay? And the 1 over u times u squared would be u is equal to x stays x, and this would be, it's just x. And look at that. That's a linear equation in u, not in y. It wasn't in y, but it is in u because of that substitution. Okay? Now, here we can go to town on this. Remember, this is our p of x. Remember, or include the minus sign. So p of x is equal to minus 1 over x, right? And what do we do with the p of x? We integrated that dx. So you integrate this dx. So that integral of that is minus log x. And we don't do a plus c on this one. Remember, we never do. Okay? Now, I want to write that as log of x to the minus 1. Remember, you could do that on the principle of logarithm. Because what did you do with this? You did the e of it. And if you do the e of this, now you get your integrating factor to be x to the minus 1 or 1 over x. Okay? That's the integrating factor of that linear equation right here in u and x, not in y and x. So we take that integrating factor and multiply it by each side. So what you get is 1 over x du dx minus, okay, 1 over x squared, because you already had a 1 over x there, u, and then when you do 1 over x times x, you just get equal 1, which is okay. Now, what we're supposed to have here, this is supposed to be a perfect derivative. Remember? Oh, and here's... What's that? Huh? Oh, yes, I just, your spirit was here, but I miss seeing your spirit. When I called your name, I didn't do it in spirit language, so your spirit didn't understand me. Okay, so never mind. Okay, that's getting really deep. Okay, this is supposed to be the derivative of your integrating factor, which was 1 over x, remember? Yep, that was your integrating factor. 1 over x times u. And let's see if it really is. Somehow my u disappeared. Okay. Well, derivative of that, I always check this to make sure, is the first, 1 over x times derivative of the second, du dx. Yes, that's right. Plus derivative of this, which is x to the minus 1, that would be minus 1 over x to the minus 2, which would be that, times this. Yes, that is perfectly it. And this then should be, yes.
How come they do it for 1 over x is 1 over x?
Okay, what's the question?
1 over x is 1 over x.
I still don't understand the question.
It seems to me like you said derivative of 1 over x is 1 over x.
No. He's using the product rule.
Okay, yeah.
You have the first one times the derivative of the second, plus the derivative of the first times the second.
Yeah. When you multiply through by the integrating factor, you're supposed to come out with a perfect derivative here. And it's supposed to be the perfect derivative of the product of your integrating factor times u. So I say, is that indeed true? Is this equal that? That's the question. That's all I'm checking. Well, by the product rule, derivative of a product would be the first times derivative of the second. That part's right. Plus the second times derivative of the first. And derivative of x to the minus 1 would be minus x to the minus 2. And that's what that is. So yes, this is a perfect derivative, and this is equal to 1. So what do we do with the perfect derivative? We integrate it. And we integrate that. And this will be dx, integrate with respect to x. You can do this with respect to x too, it doesn't really matter. Well, the integral of a perfect derivative is, the integral undoes the derivative, derivative undoes the integral. So this is 1 over x times u is equal to, and the antiderivative of 1 dx would be x, right? Plus c. We might need to adjust our c at some point, but for right now we're okay with that. Okay? Well, what we want is u, so let's multiply both sides of the equation by x. Okay? And that gives us u is equal to x squared plus cx. Okay? But we really don't care what u is, we want what y is. Well, u was 1 over y. So now we got 1 over y is equal to x squared plus cx. Okay? All we have to do is invert. And this would be y is equal to 1 over x squared plus cx. And that's your one parameter solution to that differential equation, the original one we had up there. Let's see if this agrees with the book. Y is equal 1 over
Negative.
a negative. Where did I lose my minus sign?
I think from the derivative when you was taking the derivative.
What's that?
I think it's when you was taking the derivative. Because you have a 1 over x du
Yeah.
dx minus 1 over.
Yeah. Well, no, but I put x to the minus 1. That's what made it 1 over x. Okay. Oh, but it's there. Wait. You're right. It's right there, but where did that come from? We multiplied everything. All right. Okay, that was the integrating factor. So we multiply everything on both sides. Oh, they say it's even up here. So it may be earlier we missed it. Because they said du blah, 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 is equal to minus x. And I think it was, oh yeah, I'm sorry. Remember, here I said we would multiply by, okay. Let me go back and find it exactly where that is. Okay. I've gotten lost. I'm all over the page here. Okay. Right here, I remember that was a minus and I made it a plus. Because the integrating factor, no, it was before the integrating factor. Yeah, right here. This is where it was. That became a minus here. This minus changed that to a plus. This minus, I didn't. That was where it was. So because of that, when I multiplied by 1 over x, that came out of minus 1. That's a minus 1. So I could have put the minus over there. So this became minus x squared plus c. Yeah, that's it. No. It's minus x, and then when I multiplied by x, it became minus x squared. Okay, so yeah, that's where it came from. You're right. It was there, but it's because right there I did multiply by the minus. Okay. So it came out 1 over a negative x squared plus cx. All right. Now, remember that c could have been plus or minus, so it could have been a minus cx2, then factor out the minus sign, so it could have been minus 1 over x squared plus c, if you cx, if you want to do it that way, but this is perfectly fine. Okay, now, what do you notice here? X obviously can't equal 0, okay? So if this were a, yes sir.
How you doing now?
Good thing.
Yeah, I was going back to the house.
Sure, oh absolutely.
Yeah,
Both students.
The reason why I came is it expires on the 25th of March. I mean, 15th of March. It's close to this Friday.
Right.
Yeah. Y'all want to make some money by doing research from May to July 26th, May 19th, July 26th. You can apply.
Okay.
Material science engineers, electrical engineers. So, y'all, I'm going to leave it here if you like to take a look at it.
Okay.
Just pass it on.
Okay.
And get a tack or something, maybe we'll tack it to the board.
Right.
So
Okay.
everybody else might see. Sorry to interrupt.
No, no problem. This sounds like a great
don't know.
opportunity. Right.
All right.
Yeah. Not that either of these students want any money, but
Yeah, I got plenty.
yeah. I married money, so I'm not. All right. All right. So that's what it turned out. But one thing you'll note, number one, x can't equal 0, obviously, and neither can x equal c if you factor that out. So, so you wouldn't want your x to be c, which is whatever constant you chose to have there, and that couldn't happen either. So, let's see, back to the original equation. Yeah, that makes perfect sense too, because remember the original equation was x dy dx. Well, guess what? If x was 0, you wouldn't even have a differential equation here. So yeah, that would make perfect sense for x not to be able to be 0. Now the c part, you'd have to fiddle around with that later, but yeah, this problem, obviously, x can't be 0. Well, first thing you did was divide by x, and you couldn't have done that anyway. But the problem wouldn't have made any sense if you had no differential here. You'd have just had y is equal to x squared y squared. Well, that's is an equation, but it's not a differential equation, because if you had x equal, well, and if x is 0, I'm sorry, y is equal to 0, then you have 0 is equal to 0. Ah, that's a really interesting equation. Nothing's equal to nothing. Okay. Now, that was the Bernoulli equation. All right. Bernoulli equation needs to be of the form of this. dy dx equals some function of x, y, looking just like a linear equation on this side. On this side, it looks just like a linear equation, except you have another y to some power on the right. So, now, the next type of reduction we're going to do is reduction to separation of variables. So here we have a form, dy dx, there's, makes it, I can't write, okay, that's a dx down there, is equal to some function of ax plus by plus c. Now, way back in the old days, we called that sort of like your standard equation, not quite, for a linear equation, okay? So in other words, some function of some linear expression of x and y, okay? Which is sort of bizarre, okay? Now, it can always be reduced to an equation with separable variables by means of the substitution. And if you're wondering what to substitute, let's see, what can we do? Let u equal ax plus bx plus c, okay? Now, remember the steps we had to go through before? We had to do what dy dx is, okay? So dy dx is going to be dy du times du dx. Remember that? Okay. So, this is the setup and go. This is going to be really easy. When you do substitutions, it's going to be a f of u. So that's fine. Okay? But this side is going to be a little messier. There is a u down there. Okay? Well, what is dy du? Well, that doesn't matter. That's what we're going to wind up with. What is du dx? Well, du dx, this is dy du, and du dx is a. Just capital A. Wait, that's a y there. Plus b times dy dx. Okay, you have to do a, du dx is of this thing would be a plus b times dy dx. All right. Now, on this form, all they say here, this is separable as long as b is not equal to 0. Okay. Now, you might ask yourself, why do they say that? Well, if b were equal to 0, you wouldn't need this form, because then you have to have some function of x. You can forget about what a and c are. That's just a function of x. dy dx is some function of x. Yeah, you could do that by separation of variable just like that. But if b is not equal to 0, then you can't quite. Okay. I think you'd have to also say a is not equal to 0, but they don't say that here. So we'll leave that alone for now. Okay. But that's your substitution. All right. Enough of that. Let's use it in an initial value problem, so you can see what one of these really looks like. Okay? I need all the space is the only reason I do it. So here's what we have. Dy dx is equal to negative 2x plus y squared. Whoa, this isn't like our other one, is it? Okay, minus 7. Okay, with the initial condition that y of 0 is equal to 0. This doesn't look anything like the example above it. Okay? Now, until you do this, what's your substitution? Let u equal, this is some function of a linear expression. So let u equal minus 2x plus y. Okay? Now, do we need to do anything with the 7? Not really. Okay? So then what we have up here is, I'm going to rewrite this, dy dx, and I'm going to come back and change this later, is equal to u squared minus 7. Okay? Right? Because that's what, that linear thing that's used there, that's what we're going to let the u be. Okay. Now, here's where we need to do our work like I was just saying before. If u is equal to this implies that dy dx is dy du times du dx, right? Just like we did before. Okay? Now, what is dy du? Well, then we might need to take this and rewrite this as y is equal to u plus 2x. See, solve this for y. Now we can do a dy du. And here dy du would be sorry. Yeah. That would be it would just be 1. So this would just be 1, and this would be du dx would be minus 2. No, this would be, I'm sorry, dy du. Just leave that alone. No, okay. 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 This is 1 times. That's what I want. It's throwing me off here. Okay. Just let u equal minus the what? Then du dx is equal to minus, okay. They're doing it reverse from what we have done before. Hey, goodness gracious. Well, wonders never cease. Okay. We've actually seen 4 out of the 6 people today, so that's good. 1 came and left already, turned in the paper and left. So let me go back and approach this the way the book is. They're doing it slightly differently from what they did before. So let me see, before we got it in terms of dy dx, this time they're doing straight from here, which sort of in this case kind of makes more sense because you got x's and y both in there. So what we're ultimately going to want is a du dx to replace the dy dx, but we're going to do it slightly differently. Du dx is equal to minus 2 plus dy dx. Okay. Now the reason for that, du dx, take the derivative of this with respect to x will be the minus 2 plus derivative of this with respect to x, which is dy dx. Okay. So down here where we have a dy dx, we need to put in its place du dx plus 2. So this will be dy dx is equal to du dx plus 2. Okay. So this is a du dx plus 2, that's the dy dx, is equal to u squared minus 7. Well, let's subtract 2 from both sides, and you have du dx is equal to u squared minus 9. Okay? This is separable. Multiply both sides by dx and divide by u squared minus 9, and you get du over u squared minus 9 is equal to dx. Okay? Now we can integrate both of those. Or can we? Okay? This integration, anyone remember what technique you use for that? It's going to come out being a couple logs, you're right, but you do it by partial fractions. Do you remember that? Okay. You say this can be factored as u plus 3 times u minus 3, right? So you have, and the coefficient is 1 over u squared minus 9 is going to be some a over u plus 3 plus b over u minus 3. Right? We want to split this into something else. This is partial fractions. We took a big fraction form and split it into its components. We just don't know what coefficients a and b are. So what we do, clever little trick here, is multiply everything, and this, remember, is u plus 3 times u minus 3. So let's multiply everything by u plus 3 times u minus 3. And multiply this by u plus 3 times u minus 3. And multiply this by u plus 3 times u minus 3. Done it to everything on both sides. Here the whole denominator disappears. That's what we wanted. So we're left with 1 here. Okay? Here the u plus 3's go out, and here the u minus 3's go out. So what we have is an equation saying 1 is equal to a times u minus 3 plus b times u plus 3. Right? That's what's left. Okay. Now that's kind of too bad because I can't really solve that for a and b, except I'll use this. This should be true for any u, and this is where it sort of makes the hair on my neck stand up because I don't have any more on my head. So the hair on my neck stand on end. And here's why. We're going to say so. Let's just say let u equal 3. Why not? Okay? Seems like a nice number for u to be, right? Well, on the left-hand side, we still have a 1. On the right-hand side, this goes to 0, right? So you have 1 is equal to, and when u is equal to 3, this would be 6b. So that implies that b is equal to 1/6. Okay? Well, that works so well. Why don't we let u equal minus 3. Okay? Then this one goes away, and you're left with 1 is equal to negative 6a. So a is equal to negative 1/6. Okay? If I could read my writing. Okay. Now, so let's go back and plug in here, and we're integrating.
How did you get, or we let u equal negative 3.
Mm-hmm.
And we ended up with 1 equals negative 6.
No, a is equal to negative 1. Oh, this right here? How do we get that? If u was negative 3, then this goes to 0, right? Because minus 3 plus 3 would be 0.
Right.
So that goes to 0. You have 1 is equal to a times, if u is negative 3, that's negative 3 minus 3 is minus 6. So it's minus 6 times a. Okay? And then divide by minus 6, you get a is equal to negative 6. So, what we were doing up here, needing to integrate that thing, for separation of variables. So, that integral becomes, a was minus 1/6. I'm going to reverse the order if it's okay. I'm going to put the b first because that's positive. So this would be 1/6 times that's the b here, okay, times the integral of du over u minus 3, okay, minus 1/6 times the integral of du over u plus 3. Okay, what I did, this thing was du over this thing, and we just saw that this thing does here, so that integral becomes, this would b over u, I can't read it now, minus 3, that's a minus 3, and plus a over u plus 3. So that's how I rewrote that big integral like that. Now, if you have any doubts about whether that's true or not, let's just do it and see. 1/6 of this minus 1/6 of that. If we wanted to get least common denominators, we multiply each denominator by this. We'll multiply this by u minus 3. That would give you u plus 3. 1/6, b was 1/6 times u plus 3 minus 1/6 times u minus 3 plus 1/6 minus 1/6 u. They go to 0, but then this is a minus times a minus, will be a plus 3. So it's 3a, or 3 times 1/6 plus 3 times 1/6. Well, 3/6 plus 3/6 is 1. I'm sure not that's what we're down. So, yeah, that didn't work. Okay. So, those are our integrals on that side. And on this side, the integral of dx is just x plus c. There we'll put our plus c in. I swear this is so aggravating. Well, what's the integral of this? This is 1/6, the log, natural log, and you were right to foresee this, u minus 3, minus 1/6, the natural log of u plus 3, and that's equal to x plus c. I may want to change that a little bit. So let's rewrite this as the log of, and they usually drop the absolute values here, and I don't really know why, but they usually do. u minus 3 to the 1/6 power minus the log of u plus 3 to the 1/6 power, and that's equal to x plus c. Okay? Well, the difference of two logs is the quotient. So this log of the quotient, so this will be log of u minus 3 over u plus 3 all to the 1/6, and that's equal to x plus c. Okay. Now the rest of what we're going to do is an exercise in is just an exercise in mathematics. Okay.
Real quick, how did you come up with? I got u minus 3 equals 6. How did you get the denominator u plus 3?
Okay. The log of a product is the sum of the logs. You remember that one? Okay. So the log of a difference is the quotient of the logs. So this becomes, no, I said that back. The log of a difference is the log of a quotient. Okay, in other words, the log of this would be the log of this minus the log of that. And that's how we got there. Okay. It's just one of the rules of logarithms. Just like the log of a product is the product of the logs, no, is the sum of the logs. The log of a quotient is the difference of the logs. It's just doing it in reverse. It's one of the rules of logarithms. Don't know if they show up in this text or not. I kind of doubt it. I think they count on you having that in an earlier course. And if you still have your, let's see if they're in the back anywhere. Sometimes they have them in the appendix. What's that?
The log of a multiple is an addition, the log of a quotient is a...
Wait just a minute. I'm going to see if these are in here somewhere. No. I thought maybe they'd be in an appendix. They're integral defined functions, matrices, and Laplace transforms. They're not in any of them. Okay, what is your question?
No, I was saying the log of a multiple is the addition and the log of a quotient is the subtraction.
Say that one more time.
The log of a multiple is the addition.
Yeah, sum of the logs.
Sum of the log.
And the log of a quotient is the difference of the logs. So see, that's what this is doing. The log of a quotient is the difference of the logs. Now I put everything to the 1/6 power. I could have done these separately and then put it, but I was just running out of room, so I did it at once. Okay. Now, that gets us to this point. And the math is going to take a bit longer. Okay? And they used partial fractions. They came up with the same thing we did. And they came up with that. Now, now this seems to be almost going in circles, and it kind of is, but I need more room to write, so I'm going to try to be judicious in the selection of what I erase. I'm going to need this, so I don't want to keep that, but I don't think I need these anymore. I sure hope I don't, because that will be really messy if I have to go back and recreate all that. Okay. I don't think I need this anymore either, but I'll hang on to it just in case. And I think we just use this, so I'll erase this one. Okay. That may be all I need. Let me see. I don't think I'm going to need any of this anymore. I hope not, because it's going away now. sorry this takes so long, but otherwise I have to rewrite almost as much as I'm erasing. I think erasing should be faster than rewriting and fewer mistakes, but who knows? Okay. Now this, remember, is in terms of U's, and we don't really want the U's, but we're going to wait till the very end to get rid of them. Okay, we're going to go backwards here, and then rewrite this as 1/6 times the log of U minus 3 over U plus 3 is equal to X plus C. Okay? Now we're going to multiply everything by 6. Okay? So that'd be 6x plus 6c, which again is just a constant. Okay? And we'll leave that alone for right now. Okay? Now, what we're going to do next is take an e of both sides. When you do e of this and e of that, now e of a log undoes itself, so you got u minus 3 over u plus 3 is equal to e to the 6x plus 6c. Okay? Which can be written as e to the 6x times e to the 6c. Remember, that's sort of the, when you're multiplying same base, different exponents, keep the base, add the exponents. So that's what that did. But this is just some constant, right? So we can make that our c rather than e to the 6c, okay? So we'll just do this, okay? And have that, you know, because that was multiplied by it. Okay, should have put C1s and C2s or something like that, but it's just a constant. Okay, now let's skip this down. Now what we're going to do is multiply both sides of the equation by this denominator. So you have a u minus 3 is equal to c e to the 6x times u plus 3, right? Now, this will be c e to the 6x, I'm going to put the u here with the c, plus 3 c e to the 6x, just distributing that. And this is equal to u minus 3. Okay? Now, I want to get my u's together and anything without u's separated. So let's add 3 to both sides. And let's subtract c u e to the 6x from both sides. Okay. So what we have now, factoring out the u, we have 1 minus c e to the 6x. That's what we have here. Factor out the u's. Okay, pull it on the outside. That becomes a 1 minus 6. That's equal to 3 times c e to the 6x plus 3. All right, so let's divide everything by, no, plus 1, sorry, plus 1, yeah. Okay. But I'm going to reverse the order of those again. So u is equal, I'm going to divide everything by 1 minus c e to the 6x. All right. So what we have then is u is equal to 3 times, I'm going to reverse the order of this, 1 plus c e to the 6x over 1 minus c e to the 6x. It just looks better to write the same. That's our one parameter solution in u. But wait a minute. We don't want u. We want this. So this is, the u is this. Minus 2x plus y is equal to 3 times 1 plus c e to the 6x over 1 minus c e to the 6x. All right. So if you want y by itself, add 2x to both sides. Okay. So now we have it. Y is equal to, now let's see which order they write it. They write the 2x in front. It doesn't matter. Plus 3 times 1 plus c e to the 6x, 1 minus c e to the 6x. Done. Okay. They put the 3 with the parentheses on top and left the denominator. It doesn't matter. Okay. Now, that is your solution for any c. But we have an initial condition. So when x is equal to 0, y is supposed to be 0. So that will be 0. And when x is 0, this is just going to be 3 times 1 plus c over 1 minus c. Because e to the 0 is 1. Okay? And that's equal to 0. So obviously c can't be 1. Otherwise we'd be in a really serious trap. So the only way that would be true if c was equal to minus 1. If that's equal to 0, c is equal to minus 1. Yeah, and that's what they got too. So our final solution, and I don't know where to write it, so let me erase some more stuff here. I think this will be all I need up here. Yeah, these take forever. What's that? Oh, it is?
Yeah.
Oh, wow. We were having so much fun. Okay, let me get this written. Just the final answer, if I can find my final equation. Y is equal to 2x plus 3, and the way they wrote it was 1 minus e to the 6x over 1 plus e to the 6x. Okay. Yep, that's what we got. Homework exercises here. Any that are in the back of the book of the odds 1 through goodness gracious, 1 through 9. They say 1, okay. Yeah, 1 through 9. Any of the odds 1 through 9 that are in the back of the book. Either 11 or 13 if it's in the back of, they're in the back of the book. Any of the odds 15 to 21 if they're in the back. No. 15 to 19 if they're in the back. Do 21 if it's in the back. 23 to 25 if they're in the back. Or 27. 23 to 25. 27 if they're in the back. And then try to do 29 if it's in the back. I don't think any of the rest of them will be. We'll start next time on a numerical method. And this is it for Chapter 2. I'll try to have your next test ready next time. We may not finish the numerical method next time, but I'll try to have it ready for those of you who have turned in your first test. You can get started on the second. All right, sorry we went over, but the good news is no extra charge. Okay.
Thank you for that.
Anytime.